Okay, so today I'd like to talk to you again about the quantum nature of light, and I'd like to show you a few things we didn't see in part one. In part one, we did see that the photoelectric effect was kind of the trigger to get us thinking about light as a particle, as a little bundle of energy. We have the light coming in little bundles, and those little bundles could hit a metal and knock out one electron. One bundle, one electron. It fit perfectly. So we had a bundle of energy, HF, hitting our metal, and the electron coming off with a certain kinetic energy. This model of light being a massless, chargeless particle worked out wonderful to explain the photoelectric effect. So in this model, we now think of light composed of these little bundles, these photons, and as they travel away from the source, the concentration of these photons would lessen and the light would appear less bright. In the old model, we thought of light as a wave, and it spread out into bigger and bigger surfaces and became less bright. Old model, new model. In the new model, brightness again, dim, bright, is just a function of how many photons are present. Color determines the energy of the photon. So here's one bundle of blue and one bundle of red, the smallest possible bundle. That's called the quantum of light, called the photon. They travel at the same speed. They have zero mass, zero charge, but somehow the blue possesses more energy. Not only do they possess energy, but we saw they possess momentum. The formula, Planck's constant divided by wavelength. This momentum means that light can hit something like a solar sail and push it and accelerate it through the solar system. Light itself has momentum even though it lacks mass. We saw that light can collide like a billiard ball. So we had a photon coming in, hitting a particle at rest. The particle at rest gains some of the energy and momentum of the original photon, and a new photon emerges that has a different color with less energy and less momentum. So this Compton scattering is another great example of things that can only be explained with the particle model of light. Another one we can talk about is annihilation of matter by antimatter. So if we have an electron and a positron hit each other, they will annihilate. They don't even have to hit hard, they just have to get close, they just have to touch. They annihilate, which means both particles vanish from the universe, which means mass disappears from the universe. In that place of the mass is energy. What kind of energy? Photons, light energy. The two particles will produce two photons to make sure it balances out the momentum that was originally present. So the mass turns into energy, and the photons carry away both the energy and the momentum of those particles. Okay? So another example showing this photon model working beautifully. This photon model was developed by Albert Einstein, born in Germany, eventually moved to New Jersey, Princeton in the US, died in 1955, came up with this photon model of light in 1905. Okay, here's the problem. Einstein's model is great at predicting all those things we talked about. The photoelectric effect, Compton scattering, the production of photons carrying away momentum when matter and antimatter annihilate. The pushing of the solar sail can only be explained with this photon model. But don't forget, we also know that light can interfere with itself constructively or destructively. Interference, both constructive and destructive, is a property of waves, not particles. the interferometer and the interference that results. That's a property of waves. So there are experiments that show us light acting like a wave, and there are other experiments showing us light acting like a particle. We now think of light as having a dual nature. In some experiments, it shows its wave properties, and in other experiments, it exhibits its particle properties. So diffraction. Diffraction shows us light acting like a wave. We have the light passing through two openings at the same time, spreading back out, and interfering with each other. Particles won't do this. If we were to shoot particles through, they would just go through one opening and hit right in line with that opening. We would have two spots that line up perfectly with the holes in the diffraction grating. That's not what happens with light. Light forms an interference pattern that is restricted to waves. So waves versus particles, I want you to know light can exhibit both properties. Some experiments bring out the particle nature, some experiments bring out the wave nature of light. So if we have a light bulb and we can think of photons shooting out of the light bulb in all directions, things are going well. However, let's say we lower the power going into the light bulb so that we just have one photon at a time coming off of the light. That one photon, which way does it go? Well, we could say it goes in a random direction, and that would make us feel good. But what if we had to say it goes in all directions? How could one localized bit of energy go in all directions at the same time? It doesn't make sense. And we could see this contradiction if we take that light bulb, emitting one photon at a time, and putting it in front of a diffraction grating. Okay, it would either go through one hole or the other. But that's not what happens. If we slow down the light so we only get one photon at a time, it might hit in the spot where we'd expect it to hit for a wave. Or it might hit in this spot. And if we let it happen over a long time, sending one photon at a time and measuring where they hit, over time what will build up, and some spots get hit more often than others, but what will emerge is a diffraction pattern that is indicative of waves. So somehow that one photon was really a wave passing through both openings at the same time, but then it only hit in one spot at a time. So it acted like a wave until it hit, and then it acted like a particle. And the weird part is, let's say we made this wall out of some sort of metal that had a very low work function. When those photons hit those spots, they could shoot out an electron, which can only happen if a particle hit the metal. Okay, that little bundle of energy, that photon. So the light is exhibiting both properties in the same experiment. Wave property when it goes through the diffraction grating, particle property when it hits the wall. So unfortunately, you have to be able to hold both models in your head at the same time. All right, tomorrow we will see how much crazier it gets when we take a look at the Bohr model through this new way of thinking.